All right, welcome. So in this video, I want to continue talking about loop invariance and correctness that we introduced in the last video where we talked about the minimum algorithm. And so now I'm just going to switch our subject matter to a different algorithm, a different problem. But we're still going to take a look at the same techniques using induction to prove a loop invariant and to prove correctness. So the problem that I want to switch to now is another fairly standard problem that you've probably encountered in other computer science, maybe an assignment or another lecture that you may have looked at. This is just the problem of searching, and I've generalized it here to searching for an integer in a sequence of integers. And when I say I've generalized it here, well, any problem of searching for a name in a list of names or a word in a list of words or whatever it might be can be generalized to just searching for a integer in a list of integers. The steps, the information processing steps that you would use to search for a name versus an integer are effectively the same. And most of our search techniques, at least the ones that we use standardly, rely on on a comparison model where we maybe we have something we're looking for, and then the way I've stated that in this problem statement is we've got this target, which I call t, which is some integer, and that's what we're looking for. And in the comparison model, we're going to usually compare that target to the elements that are in the list, or in this case a sequence that we're searching through. Now that's again the idea here is the comparison model means we're going to make comparisons, and hopefully if you've already tackled this problem yourself, you know that at least without any other promises, if we want to find out if t is in this list, we usually need to compare it to all of the elements of the list. And while that's getting a little ahead of ourselves, that's getting into the algorithm for the problem, but here we are just stating the problem. So again, we've got the list of integers. That's very similar to what we looked at in the minimum problem, which was the problem we looked at in the last couple videos. But we've added this extra target integer as something we're searching for, and then the output here is sort of conditional, and this is true some of the time where sometimes the output might not exist, and that's the case here. So it's possible that we don't find the element we're looking for, and it's also possible that all we are concerned with in this search is the binary yes no answer. Is it there or not? And if so, we might translate this output in a different way to just say yes if it's there and no if it's not. But often if the answer is yes, and sometimes if the answer is no, there might be more information that we want as well. In this case, if we do find it in the list, often we also want to know where it is. That's sort of the point of the search usually. So that's the way I've set up my problem here, is the output is going to be I, the index I, if one of these values of the sequence, one of these AIs, is equal to t, if it's equal to my target. Now here I haven't stated which one. If there's a tie, if all of them are t, then any one will do. If there happens to be two, again, either of the two will do. And depending on what algorithm we bring to bear on this problem, we might break ties in different ways. And again, that depends on how we might set up the algorithm. And then the other possible output we get then is if there is no AI that's equal to t, there is no such one, then we should answer -1, which is an indication that it cannot be found or it does not occur in that list. Okay, so this is the problem that I want us to focus on in this video. But again, it's hopefully a problem that we've already encountered and maybe actually had an opportunity to develop an algorithm for. And so that's sort of the first step I've got here. Can we develop the algorithm? And then again, in this video, we're going to try and prove the algorithm correct that we come up with. But I'll delay for a future video. We will return to the algorithm later and count the number of operations carried out by the algorithm. So stay tuned for that. But for now, we'll focus on correctness. Okay, so let's see if we can do that first step there, which is the developing of the algorithm. Now, as I mentioned, that if you've faced this problem before, and if you want to make sure you don't make any errors, which is sort of critical, remember we're focusing on correctness here, then to be sure we must compare our target t to all of the elements in A. Now, what order we go through those elements is somewhat arbitrary. It's up to us. And a lot of us probably have already built in some intuition. Maybe we've already written some code for this where we say, well, we're going to go this order. We're going to go 1, 2, 3, 4 up to n. That makes sense. And in fact, that's the order I'm going to go when I write some code here in a second. Okay, but I'm just going to comment here and say that we don't have to go in that order. And then we might even be able to prove, if we wanted to on the side, that going in different order works just as well. We could go in reverse order. We could start at n, go to n minus 1, all the way down to 1. And again, we might find it if it's there, and if we don't, we will have checked all of the elements. This is sometimes called a brute force solution or an exhaustive solution. By checking everything, we check them all so we can be confident that it's not there if we haven't found it. Okay? Going reverse seems to work just as well as going forward. And then for that matter, imagine this, instead of having it as a list where an order is implied, we could think of it as more as a bag. We could just pick elements out at random, if you will. Okay, we don't want to have duplicates, so we don't put them back in the bag after we pick them out, but we pick them out at random. And if each time we pick it out, we compare it to the target, and then check again. If it's there, we'll answer the index. If not, we'll answer no, or we'll answer -1 only if all of them are not equal to the target. That should also work too. Again, hopefully putting it through our own intuitive brain compilers and through our own logic machines, we can say, yeah, that makes sense. It doesn't really matter what order we do the comparisons in. What seems to matter is that we just compare it to all of them. Okay, so my point here, why am I bringing that up, is that there are multiple algorithms to solve this problem. There are even algorithms that are incorrect. Those ones I'm not even mentioning because those ones we'll just brush to the side. But there are multiple correct algorithms for this problem. And then even among the correct algorithms, some of those might be more efficient than others. Now the ones I've been describing, starting at the beginning and going to the end, starting at the end and going to the beginning, starting in the middle and sort of randomly picking an order, all of these are probably equally as efficient with a little hand waviness to that as well. Maybe a few constants here or there are different, but they all roughly have to look at all of the elements, and that's sort of the most expensive part of the algorithm. And so all of those algorithms seem roughly the same from that measure. So then what if we have a handful of algorithms, they are all correct and they are all equally efficient, now how do we pick between them? Well, here's where we have all the freedom we want. We pick between them by just picking the one we like the best, whichever one is our favorite. And so if that's the case, they're all correct and they're all equally efficient, then pick whichever one you like. It doesn't matter. Okay. Now usually what that means is we default to the ones that are the easiest for us as humans to understand maybe or code. Okay, so think about those three algorithms that we just thought up, starting at 1 and going to n, starting at n and going down to 1, starting somewhere random and kind of randomly going through the order. Which one of those is the easiest one to write some code for? Now hopefully with your own programming intuition you're thinking, well, going from 1 to n and going from n to 1 are effectively the same. I'm thinking in my own mind, thinking like a Java or JavaScript type of code. I'm thinking, oh, well, that's a for loop of some kind. And you know what? A for loop that counts up or a for loop that counts down, there's not much difference. I'm almost going counting the keystrokes here. Which one's going to take an extra keystroke? Because that's the only thing that really matters. They're effectively the same structure. But the randomizing the order, how do you even do that? Well, you can't do that in one simple for loop without being clever. Maybe being clever you can. But you might have to randomize it ahead of time or do something else, do a little bit of pre-processing, or at least be clever, as I mentioned, at least think harder. And so that algorithm, I might already just push it to the side. I'm saying that one's overly complex. It might be correct. It might be equally as efficient, but it's just overly complex. Why introduce complexity that is not necessary? So then we might go back and say, okay, I'm going to either count from 1 to n or n to 1, and then if we have to pick one or the other, we usually pick 1 to n just because, well, that's the easier one. We usually only count down n to 1 if algorithmically for the algorithm that we're solving, it makes more sense to do it that way. For our algorithm, it doesn't make more sense to do it one way or the other, so counting up is the standard way to count, so we'll count up. So let's take a look at an example algorithm. This is just one algorithm that I've come up with to solve this problem. Okay, now the way I'm going to do it is, I mentioned already, I've kind of spent a lot of time, I'm going to be counting up from 1 to n. Okay, now the other thing we're going to do here, so that's doing the comparisons of our elements, right? Now the other thing I'm going to do here is I'm going to rely on this variable m. It's what I'm going to return at the end. I called it m because I think we called it m in the last example for minimum as well. In this case, it's just what we're returning. Sometimes I call that r for returning. Now there's another way I could have written this algorithm that returns as we go. Okay, maybe in this particular case, if we found the element, we could return it right when we find it. Now I've opted to use this kind of style. Maybe for a couple of reasons, but there's one that's important. I've opted to use this particular style instead of returning as we go because I felt that the logic that we're going to use in the proof it just was clearer. It was a little more intuitive, a little bit easier to follow. Okay, by having the return in there, I had to start making statements of, well, we've already returned, and that complicated a few things. Instead here, I only return at the end. And that makes it a little easier to talk about what happens. We only return, for instance, after the whole loop has executed. Now, these are things that I was conscious of after I tried to prove the algorithm. In fact, in a previous version of these slides and this lecture, I had a different code here. But I didn't like the proof with it. I wanted a simpler proof. So I modified it and came back and did that here. And that's something you might do as well. When you are writing an algorithm for the purpose of proving it correct, not implementing it in your machine, then it is a different purpose. And so you might make different choices. For the purpose of implementing it in your machine, for instance, we might make choices like starting at index 0 instead of index 1. But that's a different purpose. So I'm going to ignore that purpose here of changing my index to 0 because that actually complicates my proof. It makes my proof harder. I'm going to have to keep track of an n-1 in there somewhere, and I don't want to. I like how many integers are there? There's n. That's all I need to know. So starting at 1 makes it easier for me in my proof. So for the purposes that I have, which is I'm trying to prove this algorithm correct, I've chosen my notation to start at 1. I've decided to take a count up from 1 to n. And then I've also chosen to only return at the end, just because those things make it easier for me to carry out my ultimate goal, which is to prove that this is correct. Okay, so let's continue with that goal then. Okay, so here, I don't think I highlighted everything here, but again, let's just do a quick run through the code here. So again, the input is as we expected. Okay, we've got the list or the sequence and the integer. Now this m that I'm going to start, that I'm going to use to return, I'm setting it up to b minus 1. That's sometimes a standard strategy. We're going to set it up for our error value, what we want to return, and then only if we find something that confirms that indeed, in this case, if we found the target, only if we find one of these AIs that's equal to the target, then we will overwrite that -1 with whatever index it is. Now I'll also maybe mention one little side effect of writing code this way. What if there was more than one target in the list? Which one do we return? Well, we can see here it would be the one with the largest index. We'd also notice that if we counted down instead, we would change that outcome. Now that outcome only was what happened in the case of a tie. And the way the problem statement is stated here, it doesn't matter what happens in case of a tie. We haven't said what we should do in case of the tie. We just said any old I will do as long as this is true. So both those algorithms will be correct, but noting both of them might return different outputs. Okay, for the same input, they might have different outputs, which is possible for two algorithms, but it's also possible for two correct algorithms, which is sometimes something we overlook. Okay, but in this case, again, let's focus only on this algorithm where we count up from 1 to n. So again, we start out by setting our m to -1. We go through each of the elements. If we find one that is equal, we'll overwrite that -1 with an I. Otherwise, if we never do, we end up returning a -1 at the end. Now, part of what I just did there when I described how this loop and this algorithm worked is I kind of smuggled in a little proof of correctness in there. I kind of hinted at you. I said something like, and if none of them are, if we never find it or something like that, then m will still be -1. Well, that's what we're trying to prove. Okay, and again, it's fairly straightforward for this code. Hopefully all of our internal brain compilers already looked at this and said, yeah, that's going to work. So now it's time to take that intuitive feeling, that implicit feeling, and make it explicit, turn it into a proof. Okay, now remember to do that when we have some code like this, that the technique that I introduced in the last video is to prove a theorem that we've been calling a loop invariant. So a loop invariant. So remember, invariant means not changing or something that doesn't change, or specifically in computer science, it usually means a property that does not change or remains the same after we do something. In this case, it's after we loop, after an iteration of the loop. And remember, as we talked about this last day, there can be many properties that remain unchanged or are still true after the loop. For instance, my name is Chris. That will be true after every iteration of this loop. And presumably after the iteration of every loop. I have no plans of changing my name in the near future. But that property is not important when it comes to what our ultimate purpose is here, which is proving this is correct. Okay, so when we are saying what is the loop invariant for this loop, it means focus in on maybe the variables that are being used here and some of the tests that we're doing, and say what property about these variables and these tests will be helpful for me to prove the proof of correctness. That's my ultimate goal. So the ultimate goal is I want to make sure that this m here is correct when I return it at the end. Meaning it's either -1 if there's no target in the list at all, or it's only an I that satisfies our condition here. Okay, now hopefully, again, looking at this code, it seems like that's true. Can we argue it true? Okay, so it seems like since the proof, the theorem that we're trying to prove has something to do with m, the loop invariant, the property that we're looking for, should be something about m, right? After iteration I of the loop, something is going to be true about m. Okay, well, what will be true about m? Now, here's the interesting thing, is if we try and think about what's true about m all as one statement, we might get a little bit confused, because really there's two cases here. There's two things that could be true about m, and it's going to be one or the other. And so I want to focus in on that. Again, we started out this series of videos talking a little bit about logic, because here we're talking about a proposition that is a logical or a disjunction. What's going to be true of m is it's either going to be -1 or it's not. It's going to be some value of I. And it's only going to be some value of I if we do something in this line here, right? Now that's not all. So maybe we could highlight that. I feel like we've sort of got a partial invariant here. We're building it up as we go. Something about m. M is -1 or it's I. For some value of I. That statement by itself is an invariant, and it's something we could probably prove true. It would be actually a little easier to prove true than the ultimate invariant we're going to work with here, because it's missing out a little bit of something. It's something that statement alone is not going to be helpful enough to help us prove the whole thing correct. If at the end all we know is that after iteration n, m will either be -1 or it will be I, that doesn't tell us that it's correct. That doesn't tell us that it's -1 when it should be -1. And that doesn't tell us that it's I when it should be I. Okay, and indeed, what does tell us that was the problem statement itself right here. Okay, this told us m should be I if ai is equal to t, and m should be minus 1 only if no such I exists. So, oops, well, here we go. I guess I've got the little spoilers then. Let's take a look at it here then. So what is the property that we really need? Well, when m is minus 1, that's supposed to carry, the way we designed the algorithm, so if we designed it correctly, minus 1 was supposed to tell us that we haven't found the target yet. And so I want to emphasize that yet. Remember, we did this in our last video when we talked about minimum. The m variable in that algorithm was meant to be the minimum so far. And that phrase, so far, is what captured the fact that we were in one interior iteration of this loop. We are in the middle somewhere. This minimum is the minimum so far, and if I keep going with this until the end, it will be the minimum of everything. Well, the m is playing a similar role here in our search. It's minus 1 if we haven't found the target t yet. And that phrase yet is the same thing as the so far. It's saying we're at some internal iteration here yet, and if m is minus 1 at this point, then that means we haven't found the target yet so far. So this expression that I've got right here, t is not an element of a1 up to ai. Notice I be careful here, changing that I from the n. N is what we want it to be at the very end, right? If we answer m, if we actually answer m is equal to m minus 1, then we want to make sure there's no target at all. But after iteration I, we've only confirmed that if m is still minus 1, that we haven't found it yet. So none of the elements thus far have been that element. However, after iteration I, it's possible we've also gone through this line somewhere, maybe in this iteration, or maybe in a previous iteration we did. If so, we won't be in case 1 here. M is not equal to minus 1, M will be equal to some J. Okay. But again, just knowing that it's equal to J is probably not enough for us to argue at the end that it's correct. If we answer J, we want to know that J is one of the elements such that AJ is equal to T. So after iteration I, if M happens to not be equal to minus 1, if it happens to be equal to some J, then it should be equal to a J such that AJ is equal to T. Now, when I sat down and I wrote this earlier, I thought to myself, well, there's actually an additional property here, an additional characteristics about J that technically I really should mention. And if you were sort of, a nitpicker, you might say, hey, wait a second, there's something missing here. But I decided afterwards that I'm going to leave it implicit. And that just means I'm going to leave it without writing it explicitly down, because it is, one, implied by what I've already written down. So if you use a little bit of reasoning, you're going to come to the same conclusion I do. But because it does require a little bit of reasoning, sometimes folk think that we should keep it in here. And what is it that I'm talking about here? I'm talking about what J is. What is the value of J? For instance, one thing that should be implied here is J is not minus 1. That was already covered in my first case. Okay. So what values of J could it be here? Now the reason why I say it's implied is that AJ, if AJ is equal to T, it must be one of these AJs. And for instance, there is no A minus 1. So I know if we are in statement 2, and statement 2 is actually true, M is some J and AJ is equal to T, because the only AJs that could be equal to T are the ones in the range 1 to N, I know J must also be in the range 1 to N. And specifically, we could be a little bit clearer with that for our proposition here, which is that after iteration I, J should actually be between 1 and I, because we will have not got up to N yet. We will have only done iteration I. But I've left, like I mentioned, I've left that unstated here. mostly to not clutter what we're trying to argue. And sometimes some of these little technical details that are technically true or are technically important to the argument, this one happens to be important, but it doesn't really show up in the proof, so I left it out. Sometimes these little technical ones can clutter our theorems and our proofs and make them a little bit harder to understand and follow. So there's a real artwork to deciding, what to include and what not to. So here I've chosen to not include a statement about j should be between 1 and I or 1 and n, but I'm going to assume that we understand that. Okay. For instance, another thing I left not included was j should be an integer. Well, usually the way we use indexes is as integers. I'm assuming we all already understand that. Okay. All right, let's see if we can tackle the proof then. Let's go into proving this. This is the loop invariant we want to prove. After iteration I, we're either at -1 and haven't found it yet, or m is some j where j is an index of where we found the target. Okay, so this proof is actually going to take 2 slides here, mostly because it's a little bit bigger and I don't want to clutter up the slide very much. But we are going to follow the same strategy that we did in the last video, which is we're going to use induction. And so induction, actually, we're going to get a lot of practice with this over the next series of videos. So we're going to, if it's feeling a little bit, mystical at this point, that's fine, because usually it takes a couple of good examples going through your induction before you're going to get really comfortable or happy with it. All right, so let's tackle this proof now. And remember that when we're doing our induction proofs, that we always have, well, 2 or 3 parts, depending on how you want to think of it, 2 or 3 parts to the proof. Now, we start out with the base case, or the base, which is just proving the base case. It means that what we're going to do is select one value of the variable that we're doing our induction on here, I, and we're going to prove it for that simple case only, that single case, that specific case. And then we remember that the generality of the proof is supported by the second step, the inductive step, or in the inductive case, where we will prove that if it works for I, then it works for I plus 1. So those are the 2 steps we're going to do, and we're going to start with the base case. Let's start with the base case. If we look back at the code, we notice that our loop started at 1. Remember, we're counting from 1 to n. So our base case, usually for our loop invariants, our base case is going to be whatever happened before the loop, before we started our iterating. And so in this case, usually, again, as I mentioned last time, what we'll do is we'll look at the index of that loop. If the index was, say, I equals 1 to start off, that's what we had, then I equals 0 represents before the loop. Iteration 0 is before the loop occurred. So that's what I've got stated here. I equals 0, i.e. prior to the loop. And then what is it that we need to prove here? So this says after iteration I. So here we're putting I equals 0 in there. And remember, iteration 0 meant before the loop. So really we could translate this as saying before the loop, either m is -1 and something is true, or m is equal to j and something's true. Well, what happens to us before the loop? Well, before the loop, we just set m to -1. Remember, that's our initialization step. So before the loop, m is equal to -1. And since we've plugged in I equals 0 here, the set that we end up getting, I1 up to I0, well, there are no values there. We end up getting just this empty sequence here. And we don't need to know anything about t, because every integer is not an element of the empty sequence. No, there's no elements of the empty sequence. So this is, I've stated it here, this is trivially true. We sometimes also might say that this is vacuously true. Something is vacuously true if there is nothing to prove. And so here, there's nothing to prove. To show that to prove that nothing is an element of the empty set is really just the definition of what the empty set, or in this case, the empty sequence is. And so we'll take that for granted. And again, in some cases, here we're trying to learn these tools, learn how induction works. So I'm trying to spell out a lot of the details. If you were an experienced mathematician and computer scientist, and you had been working on algorithms maybe your whole life, and you were talking to, say, some other member of your field who is also equally as well trained as you might leave, you almost certainly would leave this statement off because you would expect that your fellow reader here would be at least as familiar as you are to see this is the case. And in fact, if you were that well versed, if you felt that the whole base case here itself was fairly obvious, that the audience that you're speaking to would also find it very obvious, you might just leave it out. Again, because adding in some very obvious steps sometimes adds clutter to the proof and makes it harder to actually follow. Now, of course, that's not the audience that I expect. I expect that my audience is math students or computer science students who have some experience with mathematics but are not, having operated in that field for many years. So here I've said this step is trivially true. Sometimes saying something is trivially true, well, if it's trivial, why are we mentioning it? Well, here I'm mentioning it just as a sign to point out to us, hey, this is pretty easy for us to prove. And so if you're puzzled later, why didn't we add anything else here? Well, it's pretty obvious. We've kind of got down to base principles here, so we'll move on. So base case, fairly easy. Before the loop, we set our m to be -1, and all it represents before the loop by being -1 is that we haven't found the target yet. Remember, we said that we haven't found the target yet. Well, yet means not at all. We haven't even started yet. So far, haven't found it. Okay. Of course, remember the base cases are usually a little bit easier to prove. There's not as much to prove there. A lot of the heavy lifting comes in the inductive step or in the inductive case, which is, well, how we'll conclude this proof. To do that, to set up the inductive step, or the inductive step usually has two pieces. The first bit is the hypothesis, where we're going to make an assumption. So remember, we're trying to make a proof that says something like, if it worked for I, then it will work for I plus 1. Well, the way that we're going to sort of cash that out is the if it worked for I is the hypothesis part. Here we'll say, well, let's assume it worked for I then. And that's how we start out. So the next step we have here is the inductive hypothesis. Now here all I've really done is I've taken my statement of my theorem up here. Now this is telling me what happens after iteration I. Well, in my inductive step, remember, I'm going to be concerned about iteration I plus 1. Okay, so what happens prior to this iteration I plus 1 is whatever happened after iteration I. So I've really just sort of translated what I have up here, where I had after iteration I, I've put prior to iteration I plus 1. So we're going to assume prior to iteration I plus 1, whatever we had up here is true. And so I've really just cut and pasted my statement down here. We have m is equal to -1, expressing that we haven't found the target yet. Or it's also possible prior to iteration I plus 1 that we maybe have found it in one of the earlier steps, at which case m will already be set to j. Now why is this going to be important? Well, we're going to see that this establishes in the step the cases that we can argue from. Prior to iteration I plus 1, m is going to have some value. So we're going to now use that to set up our cases. So in the inductive step, remember that's going to be for all the i's now. This is a specific case. This is a general case. That in the inductive step, now the hypothesis, here when I say by hypothesis, what I'm saying here is we've made this assumption here in the inductive hypothesis. And because of that assumption, there are some things we know. What do we know? We know there are two cases that might happen prior to the loop, prior to this iteration. Okay, what are those two possible cases? Well, I've got them stated here, 1 and 2. Either m is equal to -1 and this property about the target is true, or, this is the second case now, m is j and some additional property about j. So we're going to use those two cases now to complete our proof, and I'm just going to do that on the next slide here. So continuing here, case 1. Now maybe I'll just mention here, it looks like I've taken my cases and I've switched them around. Now why have I done that? Well, I mentioned this I think in the last video, that the proof that you're seeing here is sort of like a final product of the proof. And it's really a final product that I've kind of honed over a couple of years, because I created these slides a few years ago. I think I mentioned I've changed the algorithm a little bit to make the proof a little bit more elegant. So the fact that this proof sort of is elegant and works the way that it is due to, you know, many steps of refinement. And so again, I want to emphasize that when you're writing a proof for the first time, rarely is it this refined. Rarely do you know where you're going all the time, and so you go in a sort of a roundabout way. Afterwards, you can go back and revisit the proof and sort of improve it, moving a few pieces around, saying, oh, that was a dead end, I can just strip that out. You know, this was a clear contradiction, I'll highlight that, and so on, to reorganize the proof to make it clearer and easier to read. So why is that relevant here? Well, here I had to decide what order was I going to put my case, or would I put my cases in? Well, I typically put my cases for presentation, for my audience, for you, in the order of what I consider the easiest to the hardest. And as advice to my students, usually I recommend on an exam that would be a good order to also tackle the cases. Why? Well, you know, if you're under time pressure and you want to make sure you get as much as you can, well, the easy cases are easier, right? This is also true for problems. You do the easy problems first, right? The hardest ones are harder, right? And then for presentation, which is really what I've got here, is that, well, we want to get sort of the easier or obvious steps out of the way first, and then get down to the sort of crunchy bit, as I like to call it, the hard bit, where we need to be clever and think a little bit for the end. Usually that's the last piece, okay? So the reason I've chosen to put this case first is just it's the easier of the two. And so and when I say it was easier of the two, it was the easier from my perspective. So maybe from your perspective it's not easier. Maybe you can think of a more elegant way to prove the other one. Great. Reorganize it. Your proof might be more elegant than mine. Okay, so let's look at this case then. So here I've chosen case 1. I said, well, I've actually taken case 2 up here and called it case 1. That's fine. That's going to be m equals j. So we've already, prior to iteration I plus 1, the one we're concerned with, we've already set m to be some value of j. That means somehow in an earlier loop, we must have already found it and assigned it in this way. And we already know, based on our assumption, if this is the case, then aj is equal to t. So we haven't accidentally set it to some j previously. By assumption, we did that correctly. So if it is equal to j, then we're done. Now, let's think about what happens in iteration I plus 1. Of course, we are going to do one of two possible things. We might not change m. We might just leave it as j. If we do leave it as j, then it is still equal to a j where aj is equal to t. So if we don't change it, we're good. We don't have to prove anything. The other possibility is we might update it to be, we're in iteration I plus 1, so we're going to compare these two, I plus 1 to t, and if they're equal, we might update it. In which case, it will also be true that m is equal to a j, such that aj is equal to t. It just happens to be the case that in this case, j will be I plus 1. So the statement I have here is, regardless, no matter which of those two cases occur, okay, we could call these subcases. In a second, I will actually characterize them as subcases. But regardless of whichever subcase occurs, after this iteration, we will still be in the state where m is equal to j, where aj is equal to t. So the reason I thought state 2 was the easier case was after you found it, you will always be in state 2 again. For every iteration after, you will still be in state 2. That's what I've just argued here. We never go from state 2 back to state 1, which makes sense because once we've found it, we never go back to the state of not having found it yet, right? But if we have not found it yet, if we're in state 1, it's possible for us to move to state 2. When? When we find it. Okay, so case 1 was the easier case, saying that if we've already found it, then after this iteration, it's still the case that we've already found it. Either we just used the one we found before, or if we got lucky, maybe we updated it. We found it again. We found a new instance. Okay, next case, case 2. I mentioned case 2, I'm going to split into subcases here, but case 2 is the other case up here when m is equal to -1, so we haven't found it thus far. Remember, that's what it means for us. M equals -1 means we haven't found it this far. And this is expressing that statement. We haven't found it thus far, meaning t is not one of these elements, a1 up to ai. Okay, so it's not one of these. Now let's think what happens again. Just like before, in case 1, when we go into this step here in the code, we're going to do this comparison of ai plus 1 to t. And as a result of that, we either leave it unchanged or we update. So here I'm going to split those into 2 cases. Either they're the same. If they're the same, then this would be an update. So this is the same as this case above here. In this case, we update m equals to ai plus 1. Why? Because they were equal to each other. That was what we stated in the subcase. So after iteration I plus 1, here's the case where we've moved from the m minus 1 case to the m equals j case. We found the element in this step, so we went from being an m equals -1 to after this iteration of the loop, m will be j, where aj is equal to t. Again, as above, this j that we have here will be I minus 1. Sorry, I plus 1. Okay, so if this is the case where we did find it, then this must be the case where we didn't find it again. If m is equal to -1 because we haven't found it yet, we still haven't found it after this step, okay? So if ai plus 1 is not our target, then that means after this step we haven't found it either. Well, if it's not equal, we don't do any updates. We leave m equal -1. And then here I say combining the conditions of the subcase with the case. What am I saying here? I'm saying in the case we already know that t is not a1 up to ai. Because of the subcase, we know t is not equal to ai plus 1. So putting those together, I can restate that now, that t is not an element of 1 up to ai plus 1. So we've changed the I to I plus 1. We've added that one extra element on, which again, hopefully, we can now see very explicitly here how the algorithm is working. It's saying, well, of course, each step we are checking one more element, and after that step, we've either confirmed that we've now found one more element that's not the target, or we found it, and we've made that very explicit here, okay? So after each step, either we extend our streak of not finding it, or we find it. Okay, these were the only 2 cases we needed to consider, okay? This one, I proved both subcases all at once in this one line here. But in this case, and why did I say I proved them all at once here, is because I was able to do this regardless here. What does the regardless really mean here? It means regardless which subcase we're in. It doesn't matter which subcase we're in, we make the same argument afterwards. If you can make the same argument afterwards, then there's no point in splitting them into cases. Here, we're not. We're making 2 different arguments. One that lands us in the m equals j case where we found it, one in the we haven't found it yet case. Because there's 2 separate arguments here, it's critical that we leave these separated as 2 subcases. Okay. All right, now let's just look at our 2 cases and make sure. After case 1, we always end up back in, I guess, case 1 here, the m equals j case. After case 2, we could end up in one or the other of the 2 cases, okay? But we've definitely proven that no matter what, after the iteration, we will end up in one of these 2 cases. And that's what we were trying to prove. So by induction, we've shown that after iteration I of the loop, we end up in one of these 2 cases. Okay, again, that brings our proof by induction to a close. That brings our proof of this loop invariant to a close. And I guess I should also mention, even though we did this on the 2 slides here, this was the heavy lifting here. This was the actual reasoning that we needed to do. The previous slide, the base case has a little bit of reasoning in there, But the rest of it, the setup of the base case, the setup of the inductive hypothesis, even the setup of the inductive step is mostly what I sometimes call machinery. Proof machinery, it's extra bits that go there, it's syntax, if you will, that help the reader understand what you're doing. Okay. The actual cleverness, you know, the wisdom that you need to bring to the table shows up here. Okay. Usually in the inductive step, and in this case it showed up in the inductive step. Mostly in the second case, really, but yeah, we did a lot of argument there. Okay, I do want to conclude this video with, as we did in the last video, taking that loop invariant and translating it now into an actual correctness proof, because the loop invariant really proves a property about the loop that's helpful for correctness, but it doesn't actually establish the correctness directly. So I'm just going to add this corollary. Remember, a corollary is a theorem that follows almost immediately from some other theorem or some lemmas. And so this corollary follows almost immediately from the loop invariant proof we just completed. Okay, let's see if we can follow it. So remember, to set up a proof of correctness, we want to make sure we're general. And the general criteria means we want to have an arbitrary input, not a specific input, not one we pick, one that's arbitrary. So we don't get to say how big n is or what these integers are or even what t is. We'll just say pick any old input that we might get. Okay. Then what do we want to do? We want to apply our loop invariant. We want to say something about what do we know, because the algorithm ends at the end after we finish the loop. So I'm actually going to split my proof into two cases here, and the reason I'm going to do that, and this is something that we do in proofs where we actually have multiple output conditions. So since in one case there's one correct output, but in a different case there's a different correct output, it's usually helpful to split those two cases up in our proof. So here I'm going to say, case one, assume the target is not in the list. That makes it easier for me to argue now what's going to happen. The target, so here I've set up my assumption the target is not on the list. Now let's go say and take a look at what the loop invariant tells us. Well, the loop invariant tells us that after iteration I of the loop, if the target is not in the list, we must have m equal to minus 1. Now, why is that? What did the loop invariant tell us? It told us after iteration of I of the loop, we're going to be in either one of two states. Either we'll be in the state m equals minus 1, and t is not an element of all those lists, or we're in the state where m is equal to j, where we found it. Well, we've assumed here that t is not in the list. So we can't be in that second case. We'll never find it. So we know we must be in the first case where m is equal to minus 1. And that persists even after iteration n. Basically what we're saying here is the loop invariant is implying for us that if we don't have the target in the list, m will remain minus 1 throughout the entire loop. And thus, when we return m at the end, we are returning the correct answer, which is minus 1 in this case. Okay, now what about case 2? Now, in case 1, we assume the target was not on the list. So now I'm going to assume the target is in the list, and I'm going to assume it's equal to some AI. Okay. Now here I'm actually going to smuggle in a little proof by contradiction here. I feel like it made it a little bit easier for me. So now what I'm going to say is assume the target is in the list, but also assume that after the loop something went wrong and m was still equal to minus 1. Okay. If that were the case, then by our loop invariant, t must not be in the set at all, but I just assumed it was. That's the contradiction. Okay, this contradicts our assumption that it was. So by the loop invariant, m must be equal to I for some I where ai is equal to t. Maybe this one, maybe not. Okay. So this establishes, now remember here, in this case, we're supposed to either output minus 1, that was the first case, or I for some I if ai is equal to t. So again, in case 2, this establishes that by the loop invariant, m must be equal to I for some I where ai is equal to t, Since after this step we return M, again we're correct. So in both these cases we return the correct output, case 1 and case 2, and that's all we need to establish correctness of our algorithm. Okay, I think that completes this video, what I wanted to say about the sequential search algorithm. Hopefully an algorithm you're already familiar with or have had an opportunity to code up in some programming language or another. But now we've proven it correct, so we can be confident that it works all the time, not just the versions we've written. And then in the next video, what I want to do is, again, go through this same series of steps, but for another algorithm, and that will be an algorithm that compares to see if two strings are equal to one another. So once again, thanks a lot for watching, and we'll see you in that next video.